Hello everybody and welcome to Handmade Hero, the show where we code a complete game live on stream. We are doing some lighting today, and by lighting I mean my really weird nonsense idea for doing lighting via multigrid simulation, which doesn't make a whole lot of sense for reasons I've explained earlier, but you know, just because something doesn't make sense doesn't mean you shouldn't try it. We're on day 395 here, and we pretty much left off yesterday, that's good, left off last time with, you know, we could have just kept coding. We were right in the middle of something. We had just gotten light textures downsampling, and so I'm just going to hop right back into it today because essentially we've just got to implement a bunch of stuff and test it out, get it working to see if this lighting scheme is at all interesting. So today, again, day 395, so if you want to follow along at home with what I'm doing, you want day 394 as your jumping off point. All right. So I'm going to go ahead and load up what we had here. And just mention what it is. It's currently we've got, you know, sort of the rendering of the game is happening in the background, but we're drawing over it with just directly our textures, our lighting textures. And I made it so we could actually step through those textures and see what each of them looked like. And we're right now drawing a test red light into the center of them. So what I want to point out here just at the start, because I wanted to test one thing before we get much further into it, is that if you look at what's going on here with this red light, you can imagine how far you might want that red light to propagate in terms of diffuse lighting. It doesn't propagate very far, even at the highest level. So by the time we get out to here, you know, the red light has not gone very far. And then eventually it averages out to nothing. And so what I wanted to take a look at was just thinking about what we would do if we wanted to make this light go further out. And one of the things that is something we have to play with, obviously we can change our algorithm for distributing lighting around. But one of the things I wanted to mention is the ratio of the numbers where a light source is present in the bitmap versus everywhere else in the bitmap is what will control how far it spreads to a certain degree. So what I wanted to take a look at is what happens if you take the light source values and you make them much higher. So for example, if a neighboring pixel is 0 for meaning no light, and we have 1 for meaning light, then in terms of just the visible range of what we see, which is 0 to 1, what would happen if we boosted those lights up well above the 0 to 1 range in terms of how far they would spread? That's basically what I wanted to know. You can see here we've got our fake light seeding code, and our fake light seeding code is just going to put 1s in there, you can see. So I'm just curious, what happens if I put 100 in instead? So now when I'm creating that fake bitmap, it's 100 instead of 1. And now let's see what happens when it propagates. So it looks to me at the moment like we're not really getting proper spreading either. So I think there's something slightly wrong with our downsampling here. Because it might just be that we have to downsample at more than 2x. I'll have to think about that, but that doesn't seem right to me either. So when this gets larger, you can see that it's still at full value. So when I switch, each time I go up, I should expect to see at least 1 pixel pick up that value, and I'm not seeing that. So that concerns me a little bit, and I want to find out why that is, because I don't know why that is. So I think we just want to take a look at this here and see what's going on. I think, yeah, so I think just looking at this code here, we do have the problem that as we're going through the UVs for these things, we may not be using the bilinear sample to actually do a bilinear sample, right? And so this code really probably has to get a little bit better. Now, there's a couple things we can do here. And let me just say what I mean by that. In fact, let me see if I can find the pen amid this mess that is this desk right now. The pen for the Wacom tablet, which, you know, you would think that I would have around. There it is. All right, so allergies, allergies. Everybody loves allergies. Actually, no one loves allergies, except allergists. They'd be out of a job, I suppose. All right. Milton has lost connection to the tablet, as is its way. I need to add just a button. There just needs to be a button in Milton that's like reconnect to the tablet that we could just hit. There we go. So here we are on day 394. And what we want to do here is we want to look at multigrid up. So what we have essentially is a texture, and let's pretend it's a 4x4 texture, and we're going to go to a 2x2 texture. So when we do this sampling, the most primitive version of the upsampling we could do would need to take into account at least 4 of the lower level texels, the higher resolution texels, if you will. So if we have A, B, C, and D, that has to map to just A in this one, right? And the reason why we have to have at least 4 of these is because if we want light to be able to propagate to cells in the by using sort of this bigger coverage area at each level, we can't lose any cells. So each downsample, you know, we have to look at the contribution from all of the lower level cells when we go up to a higher level. And the key there is that if we don't look at least 4, then the collapse will be losing some cells, right? Because if we just looked at, say, the A cell, then the B, D, and C cells would not be there. 4 is the smallest set you could look at, 2 in each direction, in order to produce the higher level version. So when we do that, there's 2 ways we can do that. One is we can write our own sampler, and our own sampler would be one which just grabbed the texels and did the bilinear ourselves. Now, why would we do that? Well, the reason we would do that is if we thought we wanted to eventually do something other than bilinear, which is fairly likely. This is a weird lighting propagation algorithm. The chances that we're going to want to do something other than just a bilinear sample are pretty high. What else could we do? Well, we could just pick this center point 100% correctly so that when we are sampling A, we sample right there. Okay? And then the bilinear filter would add those up and divide by 4 for us. Awful allergies. I don't think they are all that seasonal, honestly. I think it's more like there's so much construction in Seattle, there's just tons of debris in the air, and you breathe it all in. Progress. All right, so what I would like to do, I think, is write the shader such that we are manually doing that process. And the reason that I'd like to do that rather than try to make sure that we have the sample working 100% properly is because, again, I think we might want to fuss with the math eventually. And if we don't want to fuss with the math, then maybe this will be a little bit slower because it's not using the built-in bilinear filtering. And so, you know, that's not a great decision in the end if it turns out we just end up with bilinear. But if we do end up with just bilinear in the end, it's not a big deal to just turn it back. Whereas, since I have to go do some debugging work now to make sure this propagation works in the first place, I might as well do the full bore one so that there's no cost to us in the future in changing that algorithm. So what I want to do here, you can see when we do this sample, is I want to be able to get out 4 samples, one from each of the corners. And so what I'd like to do here, excuse me, for now is introduce my own function that'll do that for me. So a v3, which is like a manual sample or whatever. And manual sample would get from a texture that is passed, right? So we want to pass one of these samplers here, right? So we want to pass a sampler 2D that's the texture to read from. Maybe I'll just call it the sampler. And then we want to do this operation. Now, to begin with, again, I'm going to start simple. Here's the texture call. I'm just going to pass in the sampler here. We have the fragment UV, and the fragment UV is going to get passed in there. And then we have the RGB on the end. So that should be about it, and then I just return that result. And now what I want to do is make sure that I'm able to do just that operation. And if I do just that operation, and I guess I should probably switch over here so I won't end up behind my head again. What I should see now is when I go look back at the game running, after taking care of any compilers and the shader, I should see exactly the same thing as I saw before, right? That's the sort of the expectation, or the hope. Looks like I accidentally left the word texture on there. There we go. And so it looks like everything's fine here, right? All of these are totally fine, so that's good. And so now inside manual sample, we want to be able to do the operation that I was just talking about. Now, the interesting thing about this operation is that we essentially have we may at this point not need the frag UV anymore because of the way that we're going to do the sampling here. Although I'm not really sure about that because, again, we sort of have this problem where we're downsampling past the point where we can actually guarantee that there's a 2-to-1 ratio. I would prefer it if there always was a 2-to-1 ratio, and maybe we'll have to enforce that in the future, but right now I guess we're sort of still trying to get away with not doing that. Anyway, so let's go ahead and see here what we can do about that. So if I take a look at my OpenGL docs, should have left them open. What you can see is that right now, here's the page where we can see all the textile operations we have. And the kind of texture fetching that we've been doing is this kind over here. But remember, I think we mentioned this before because we used it for when we were doing the depth peeling stuff, or at least tried to use it at one point. I don't remember what we ended up settling on for that. But there's a thing called Textile Fetch. And what Textile Fetch does is Textile Fetch will produce for you a specific texture sample without any adulteration. So it'll just get back a texture literally. And when it does that, what we will be able to do is take neighboring samples and get their exact values so that we can average them using our own math if we want to, right? Now, the thing about this that's a little bit confusing, right, is when you do a textile fetch, you have to look up directly into the texture. What that means is you have to pass, as you can see here, the actual textile coordinates that you wanted. Now, that is easy to do in some sense if you know what the size of the thing is that you're looking into, but harder if you don't. And so that's why I say if this was always 2 to 1, it would be a lot easier. Now we can start by doing it just 2 to 1 and see what happens. But the problem, like I said, is just going to be that when you get, at some point you get to a place where the downsample doesn't quite go 2 to 1. Now, as I'm sort of saying that in my head, the thing I'm realizing too is I wonder how much of that is a problem here, where at some point we end up below the level where we're going to be 2 to 1. So we go into a place where we're actually not mapping exactly. Because again, we know that 1920 by 1080 won't have that be the case. What I was thinking is, you know, if we wanted to, we could take that out of the equation by forcing the lighting at the moment to always be something that isn't 1920 by 1080, right? Because when we do our lighting, we could choose to do it on some other grid that's not the same as the resolution. So if I want to, for example, I could go and, what's the setting? Here it is. I could go and force the lighting texture, width, and height to be something else, right? So suppose I always picked 1024 by 512, for example. In that case, right, now I've got so that I'm always downsampling by exactly 2. Now it's not going to be, when stretched to the screen, it's not going to be square pixels, right? And you can kind of see that happening here. And so as I kind of come out, yeah, so you can see actually in this case exactly what I said would happen did happen actually. So the problem was not the bilinear sample there, I guess. It was just the fact that we eventually got down below the 2 to 1 ratio. So that's good to know, right? Now, what I'm not sure about is why we don't eventually get to a place where we've got the whole screen filled there. So that's a little bit weird to me. So I'd like to investigate that a little bit further. But now at least we're propagating the light out in the way that I had wanted it to do. So it's a little bit better, right? That's what I wanted to see, is having it eventually go to fill the whole screen. And so now if I go back and switch out of doing the 1.0, sorry, the 100 strong version, and I switch back to just doing a emission of 1, right? So now we can see how far it propagates. We can see a little bit better. It propagates quite far still, right? So that means a light with a power of 10 in our made-up units. Remember, these are not lumens or anything. We're just playing with just a value that means something only to us. A light with power 10 still affects like that much of the screen, right? And that's exactly what I wanted, right? That's exactly what I wanted. So now the question is, I guess we don't really need to worry too much about the upsample process now, which is good. Let's also take a look at some of these other ones here. So you can see these are like our other reflection, pieces of reflection information. And that all looks pretty good too, right? All right, so that's all good. So yeah, what I'd like to do now is potentially start fussing with that math. Now, again, like I said, why do we want to fuss with the math? The reason I want to fuss with the math is because I think we're going to need our own versions of it. And even just looking at it now, I realize I think we do have something already where we would want to fix. So if you think about what's going on here, we are trying to mix light sources together. And in order to mix the light sources together, what we need to do is we need to do stuff like say, well, if a surface was pointing, or an emitter or whatever else it was pointing that direction, in this case it's emitter on the up pass. If an emitter was pointing that direction and another emitter was pointing that direction, then when we blend those together, if this emitter was much stronger than this emitter, we don't want to weight them equally. We want the stronger emitter to take more of that, to be more dominant, right? So when we do that blend, what we want to do is weight the blend by the emitter. Now there's two ways we can do that. We can either pre-multiply the values or we can weight them during the blend. The reason weighting them during the blend might be better is because it could lead to smaller data for us. The example is right now we only need an RGB texture for our NX, NY, D, which is the pack texture that has the normal to the surface X and Y in it. Well, the normal X and Y can only be expressed in two values if we a priori know that they're always going to be normalized. So NX, NY, and Z, the NZ can be recovered from just the NX and the NY only in the circumstance where we know that they, the length of this thing is 1, right? Because then we've got something to solve for. If we can't do that, then we have no idea. Should get rid of this. Milton really did not like having that run in the background. I was taking up all the GPU time, or CPU time, not sure which, probably GPU time. Anyway, so if we want to do stuff like that, then we have to do the blend correctly. We can't just pre-multiply these values by the strength of the light and have it come out in the wash. The alternative, again, would be to do NX, NY, and ZD as an RGBA. Then those can be pre-multiplied by the strength of the light, and the blending will just work. So again, options there. I'm not sure which one we want to do, but we have to do something, right? And the same would be true for the reflectance of the surface, I guess, if the surfaces were bigger or smaller, which are not really. So I think it's really only the NXNY that I can think of at this point that would actually need that. So that does seem like at that point, if that was the case, if it's only the NXNY, then maybe, for the sake of preserving our ability to potentially still use the bilinear hardware, that does have me kind of thinking that maybe it would be better if we just expanded NX, NY, and ZD to an RGBA, because at that point we could still rely on the bilinear filter to do the work for us, and that would be good. Well, I'm going to go ahead and I think implement this in the bilinear downsample sense. I would also like to know, I think here's the other thing that probably we want to do to keep ourselves from being in trouble here, and I didn't do it. I wasn't careful about it before. So the other thing that I think we want to do here is, as the light indexes, light buffer count stuff is happening where we're going successively smaller here. When we do this text width, text height, we're dividing it by 2, and what you can see there is when we do that divide by 2, it's a destructive divide by 2. So what I mean by that is, let's suppose we divide by 2 down below the level where we would be doing 1-to-1. Now, I did isolate it, like I said, to doing just powers of 2 here. So we know that now we're not getting a problem where we're not taking enough samples at some particular level. But if you imagine we were doing 1920 by 1080, right? Then what you can see happen there is, if I look at 1080, that's the one that'll blow up first. I divide by 2, I get 540. I divide by 2, I get 270. Divide by 2, 135. This is no longer even. So when I divide by 2 now, I'll get 67.5. Now, if I were to round that up to 68, then I would still be able to divide by 2 and know that the 68, right, the texture that's 68 long, would still have at least one sample for every 2 texels in the 135 texture, right? However, if I round down to 67, then at least in one place we're going to skip a texel, right? We're going to have a place where we're sampling only from one texel instead of two texels. That just has to be the case, right? Because we don't have as many samples as half the number. We have 0.5 less instead of 0.5 more, right? And so you can imagine, you know how this works, right? Let's say we took a 4 wide texture, right? We said instead of 4 wide, it's 5 wide, okay? And now we're going to represent that in one of two ways. One way, we're going to round the half up. So we're going to say we're going to map it to 3, right? Well, how does it map to 3? It maps to 3, like roughly, right? Like this. Okay? And what you can see there is for any given texel, we have at least 2 things it could map to when you take that sample, right? So if we wanted to guarantee that we always had a new sample for every 2 samples, we would. So the thing we'd be introducing is some texel would actually be able to touch 3, and we'd have to come up with just some arbitrary rule for picking which 2 it used. But we would never have the case where it wouldn't. On the other hand, let's say we pick one where we've got 2. Well, in this case, we've got more than one texel that has 3. So whatever we pick, we'll never be able to get all of our texels. For this one, we would. These 2 go to here, these 2 go to here, and these 2 go to here. And we oversampled this texel. So the only bug is oversampling. In this one, we have the opposite problem. These 2 go to here, and these 2 go to here. We don't have any way of sampling this middle texel. This middle texel just got lost. Now, normally you'd think that's not that big of a deal. In our case, where we're counting on this to propagate light, it could be huge. Because if that's the only texel that's recording the information for a very powerful light in the scene, and that isn't picked up, we get a flicker on that frame where that light goes away entirely at the high level of propagation. And we don't want that, right? So what we probably want to do here as well, like I was saying, is when we do this divide by 2, we probably want to do a safe divide by 2. So what we probably want to do is a text width plus 1 divided by 2. So that way we're always going to keep ourselves at an even divide down. And we're never going to get into a situation where the texture would drop below that sampling boundary. Okay. So here's that process again, right? That operation will not affect the 1024 by 512. Let's go back to using render width, render height for a second, which is not 1920 by 1080. It's 1 drop below that because we were rendering at a lower resolution. And let's see what happens here. So yeah, you can see now we've got it so that it's actually working correctly even at the render resolution. And that was exactly what I had hoped to see, right? So I think that was our only problem is forgetting that fact, you know, that we had sort of a problem, yeah, with that aspect of the situation. So what I'd like to do now is go ahead and try doing this propagation, the sort of the final downsample version, where after we propagate the stuff up, we also propagate it back down, right? So now that we can look at the up propagation and it looks like what I want, we could do the propagation down. Now, the other thing we can do, like I said at this point, is fix the blending so that lights get averaged properly. At the moment, we don't really have to worry about that because we only have 1 light. But we will have to fix that when we add a second light source, right? So we could do either of those. I guess, yeah, it's hard to decide. I guess let's just go ahead and try to do... let's try to do that process where we manually sample and we'll weight by the light intensity. right? And the way we could test that is, so here is, I believe, the NZ map, the NZD map. So the NZD map is the thing that needs to get that weight distributed to it properly. So what we could do is make two lights, one weak and one strong, that will, hit each other in the blend, and we could then, see if they properly combine the way that we think they should, where the strong one will dominate in the successive blending, right? So what I want to do is my fake seed lighting here, I want to update the fake seed lighting shader so that now when it does this distance to light thing, it can do multiple of those lights. And so I want to be able to do that, I want to be able to do that pretty easily so we can add lots of lights into our test eventually, because we want to be able to test a number of things before we get to the point where we're actually getting lights from the real render, because again, it's much easier for us to debug it in a, sort of this fake way where everything is under our control and constructed very carefully than it is once we start throwing real data into it. Because once we throw real data into it, it's really hard to know what's right and what's wrong. Sometimes you can maybe think something, if it's close to working but not quite right, you're not going to be able to see those errors, and you're just going to have subtly wrong lighting instead of getting to that really nice, crisp, correct point. So what I want to do here is just make a function called light, and what that'll be is it'll take this sort of data. Here we go. And I'm going to have to make these globals. I believe that's allowed. I don't know if it's actually allowed. I hope it's allowed. I'm going to make these globals. And what light will do is it's just going to do that same operation that we were doing before, but it's going to do it with parametric position for the light source, size of the light source, and strength of the light source. So in this case, we need a light P, and you can see that coming in here. And it doesn't need to be X wide anymore, so here we'll just do light P. And everything else here should work as expected. We just want to sort of add some stuff in here. So when we take a look at the light radius, and we want the light strength, so we want basically a light radius. We want a front emit, we want a back emit, we want a surface color. Actually, we'll just leave surface color as 0. And we want a so this is actually good that I'm looking at this. So where there is lighting, the surface color also, you want to ignore anyone who has lighting information. You want to make sure surface color is only blended from things that are going to reflect light, not just emit it, right? So that's another place that we might find that our upsample needs to be smart, right? So that's another good reason to do the upsample. So anyway, here's what we want all of these values to be. So this is like the light front emit, the light back emit, and the light NP. And what we're going to do is replace all of those. So in here where I call that, oops, I got a little bit overzealous there. We're just going to pass those values that we were setting before exactly as they were. And now we just need also that light radius. So that's 10. So now we're passing the light radius, we're passing the front emit, the back emit, the light NP. We don't need the surface color at the moment. And there we've got our light. We also can now say, all right, with our front emit and everything else, I can now change this to using the ones that are passed in. Oh, wait. We decided that one's just 0. And so that's really all there is there. So let's do fix compile errors in that. What are they? Can you tell me? No matching overloaded function for light. There we go. And so there's the light source. Looks all good. And now I should be able to freely just add a second one in here, where maybe I'll just take whatever this is and add, move it over slightly, and I'll make this light significantly less powerful. So this is like a super weak light or whatever. So there's my two light sources. You can see the weak one and the strong one. I think since I want them to collide rather violently, what I want to do here probably is say, well, you know, as these two collide, let's make sure that they're both strong enough to be interesting. So I'll make one 10 and one 100, like so. Oops, that's not right. Oh yeah, no, that is right. So that was 10 and that was 100. Let me just move these up so they align. There we go. So yeah, let's take a look at those, and I'll also make this one have as a D value of 1. And I might as well make them different colors. So I'll make the weaker light green. And red, so the polarity of them basically flip. Or maybe I'll make it blue so that it's clear which texture we're looking at and I don't get confused or something. Why did that go? I shouldn't have modified that. That's just the displacement. All right. So now as we go, yeah, so now it looks roughly correct. In the sense that it appears to be propagating that light out reasonably well. I am a little troubled by the green motion there, but I guess it's okay. Yeah, it's just because of the weird non-power of 2-ness of these textures. But that looks pretty good. So what you can see here is that even at that, I think they need to be a little closer together for me to really do this test, because the other one's still a little too weak and blends out a little bit faster than I would need it to. All right, so what you can see here is these lights blend relatively correctly. I mean correctly for some weird definition of correctly, since this is a weird system that doesn't have units. But you can see how that at a certain level, they're both powerful enough when they're propagating. Remember, we can't visualize these light values properly. So at this point, they're both clamping off the end. But you can see the green is much more dominant, because as it continues to blend, the green value is the one that persists, and that's because, again, here, you know, they're both at, like, you know, one of them's at 30 and one of them's at 3 or something, right? But as they go forward, you can kind of get that sense, right, of the green is a higher value, so it continues to preserve itself, right? So what we want to do, though, is focus our attention more on like this. So if you take a look at this, I will say I'm not sure why. So looking at this, I'm a little confused. The surface color is 0 where the light sources are, so that that bitmap looks like I would expect it to. No problem there. But the where is my actual editor? Did my editor just get closed? Thanks. Must have hit Alt F4 one too many times. Let's try that one more time. All right. So everything looks correct to me except for one thing that I'm a little confused about, which is looking at this bitmap. Oh, I know why. Because everywhere else we are saying that the normal is pointing up. So I need something that's not going to look like that. So that does make sense. However, if we look at it here, in this case, my NP, right, my light NP here. So I should be seeing 0, 1, 1, which is cyan. Is that what I normally set everything to by default? Oh, okay, I do. I set 0, 1, 10. All right, well, that's just the way it goes sometimes. All right, so let's suppose I wanted to sort of make something that would make more sense here. What could I do? Well, I guess I could set it to point the other direction, which is like -1 or something, which would make it harder to view it, but would probably work. I could also just say, for the sake of an argument, let's suppose I blacked out the rest of the area for now, even though that's not realistic at all, right? All right, so you can see how this one's blending, and you can see how I'm getting exactly what I said I don't want, right? Which is that I've got a bright light next to a less bright light. And they're unfortunately a little bit overlapping at the moment, so maybe I shouldn't quite have them be that close to each other, but I want them to be almost that close to each other. There we go. So when I take a look here and these guys intersect, what I want to do is I want that information about the normals for that light to be persisting properly, right? Because right now they're not. And what I guess the thing that's kind of bugging me about this is for surface reflectors versus surface lighting elements, I do wonder a little bit about how this is really going to work, because you know, we're kind of treating this in such a strange fashion. When you do the lighting transfer, you know, you're going to be looking at, if the lights always predominate the surface shape, then you're going to end up in this situation where yeah, I guess maybe I really don't want that. As much as it sounds weird, maybe I really just want to keep it doing just the averaging. See, the dilemma I'm having here is that, you know, if you think about what you'd want to have happen, is you've got, you're sort of treating these things as you get further and further up the chain as more and more averaged versions of sort of a piece of geometry almost, right? So, you know, as you go up, you're trying to compute what the average facing direction of stuff in this area happens to be, so that you can figure out how much transfer is happening to that area as a whole. Now, the problem with that is that the light direction, if you treat it as one piece of geometry that is both is emitting and receiving light, then you end up with the light, you can't use the light direction and make it predominate because you would lose the information about the reflectors in that area. So it makes me wonder a little bit whether the smarter way to do it is to have an addition 2 textures, one for the surface direction, like we have surface color. And so you've basically got, you know, emission color, emission direction, and surface color, surface direction. And, you know, you kind of you kind of sum them separately. And I really don't know. That's something I'm not super sure about. Like, I don't have a good idea. I guess what I'd say is, since we probably want to try both, I guess we should try it this way first. Because since we don't really know what we're dealing with here, it'd be premature to say. I mean, you know, they're both sort of just approximations to something. One is a more crude approximation, potentially. But, you know, if they're already, both of them are crude, so I don't know what to say about that, really. So I guess we'll just continue forward along this path. So I'm going to restore this to being, I think this should be -10, actually. And so these will be -10 pointing upwards. So they'll be kind of dropped back a bit. That would also let me see them more clearly. So there you can actually see the lights versus the backdrop. And there's the surface reflectance. There's the backside emission. There's the front side emission. All right. Okay. So now what I want to do is I want to start looking, I guess, at the downward propagation part of this. Because we now do produce averaged versions, we are not doing anything special with the upsampling. I'm literally just leaving it as bilinear filtering for right now. Now in the future, like I said, we probably want to do something different there, but at the moment, that's what we're going to do, right? Okay. So we need to create another shader now. And this shader, the multi-light down shader, is going to do sort of a similar process, but it's going to have a ton more code in it. The multi-light up shader is a pretty cheap, pretty uninteresting shader. The only thing about it that's a little bit out of the ordinary in this case is just the fact that it happens to write to more than one target. So to the extent where it is, to the extent where it has anything particularly odd about it at all, that's what it is, right? So when we look at the compile multi-light down shader, this is really the one that's going to do all of the work. And so this one's going to be much more expensive, although it's going to write to less textures. So instead of having an out where we're going front emit, back emit, surface color, NP, the surface color and the NP are never going to change. We can't change the color of surfaces. We can't change the direction they're pointing on the way down. All we can change is how much light got, we're saying is bouncing off of them, which is the front and back emit for those surfaces. So we're going to see something like this, where we're going to be writing our dest front and dest back emit out in this to these two, and then the surface color and the NP are only going to be sources, right? So there's only going to be sources for that. There's not going to be anything else. And so the way that we are going to propagate this down is a little bit hard for me to say how we want to do it. But effectively what we want to do is we want to take the higher level texture and we want to propagate the lighting down to the lower level. So let's think about this for a second so that we know what we're going to try to sample here. So if you imagine us having a 4 wide at the highest level, if we had a 4 wide. Now there technically is even a 1 wide version. And so if you think about what we have to do to make this work, we're going to be talking about something that goes successively down from like the 1 to the 4 to the 8, or 16 rather. That's drawn very poorly. There we go. I'm like, why does that not look like 16 to me? Because it's not. So when we look at what's happening here, for a particular textile, say this textile here, we have to go figure out, and maybe I'll make it a little bit simpler. So for this textile here, right, I'm going to be looking up into this upper level texture to try and figure out what's going on with like the surface emission, right? And then I'm going to use that information to adjust what I have on my own texture. Now, the thing is, I really want to be doing some reflection at my own level as well, I think. So this is why I sort of was talking before about how we might want to have different textures for the route down. Because what I'm thinking is, we probably want to actually do the light propagation step such that we read from both our level and the upper level. So we look at the upper level and we suck those results down, right? And then we look at our level and we compute our new value from both that value we suck down for the wider area and looking at the reflectance we get from our neighbors, right? And we can do that in as big a kernel as we want. So, you know, we could even choose to do it on a 3x3 basically, like to fetch sort of around the boundary there. And I guess what I would say about that is I'm not super sure I'm not super sure which of those we need to do. I would think that we would have to do them I would think that we would have to do them on something that was going to be propagating in a neighborhood fashion like that, right? Like I would think that we would have to do them where we were sampling from we took 9 samples and did the computation for the center sample based on the 8 surrounding samples. Because otherwise, I feel like you're never going to be able to get the propagation to be fair in all directions. So that seems like what we would have to do. So for every cell in the destination texture, we would sample the 8 surrounding textiles. And we would use the data from the 8 surrounding textiles to compute the value for this textile, and we'd write it back. I don't really see anything else we could do besides that. So it seems to me like that's what we're looking at, right? I mean, that is the situation. And presumably from that, that computation is going to be sort of following what we said was our basic idea for computing the lighting, which is to say that we have, where's that little diagram? How come we can't get the diagrams here? This is not what we want. How do we end up on fluid flow? How did we end up on fluid flow, folks? Well, in theory, we should be able to find it here again. History. Is it this one? I mean, how did we lose this? We had it up, and now it thinks we were always on that page? How does it think we were always on that page? That doesn't make any sense, does it? Here it is. Man. I should just remember Michael Bunnell. Or Bunell. I don't know how to pronounce that. So this is the computation that I said we were going to try using, which is just if we've got two reflectors, we go ahead and say, here is the approximate transfer between them, right? So you can see that this is not a particularly complicated expression. Basically what they're saying here is if you take the vector that connects the two surface elements that you've got, then what you want to do is say the cosine of the angle of the emitter's normal to that, which again is just going to be a dot product, right? Because you imagine we've got this line and we've got the emitter's normal. So basically this is just a dot product. So it's 1 minus the length of this line times the dot product of the emitter versus the line times the max of 1 and 4 times the cosine of the reflector and the line divided by the square root of the area over pi plus R2. And so in our case, the area in question is like they are modeling the area of these reflectors because they're actually treating them as individual points in the world. We aren't. So we don't have an area for the emitter. It's just assumed to emit, right? Like the area of the emitter and the area of the receiver are always the same. And so we don't really have a term that's going to change the amount of light that gets projected onto it based on that, because these two things scale separately, right? Now what I don't see here, what I don't see is I don't see the area of the receiver anywhere. Here we go. Oh wait, no, it's already distributed pi. So I don't know. So I guess they're factoring that out of the equation entirely. I guess because they're just computing the. Well, actually, I guess I don't know. I'm not sure I know exactly why that wouldn't be at least somewhat relevant, but I guess the size of the receiver doesn't really matter, because it's like, well, the light is falling on this thing. It doesn't matter how big it is. It just matters what angle it's falling at, I guess. So either or. In this case, our emitter area, like I was saying, our emitter area doesn't really mean anything in this case, because we don't have different sizes. So yeah. And this is, oh, I see. Never mind. This is their shadowing equation. I'm looking in the wrong part. I was just looking for their transference equation. But that's their shadowing equation. So do they talk about their transference equation here or not? So which way? All okay. Image is useful to blah 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 blah. It involves calculating the accessibility value, which is the percentage of the hemisphere above each surface point not occluded by geometry. Sure. This should be also used to calculate the direction of least occlusion, calling the bent normal. The bent normal is used in place of the regular normal when shading the surface for more accurate environment lighting. So that's basically saying, well, you should look in the direction that you're not getting shadowed, because hey, that's where most of your light's going to come from. And sure, that makes sense too. But yeah, I just am not sure. So they're talking about the shadow approximation here, which is to say that that's where the 1 minus comes from, right? It's saying I would normally have 100% of the light incoming, but for any given other person who might be blocking me, here's here's the equation to see how much of the angle of the sky they are taking out. And as they pointed out, in this case, they don't know how much two occluders may be shadowing each other, like this, for example. So given that fact, they try to use that to, they try to use how much somebody was shadowing in a previous pass in order to mitigate those effects, right? So since A is shadowing B in this case, C would pick up less of B's shadowing effect for ambient occlusion. But again, so that part is not really the part I was interested in. Indirect lighting and area lights is the thing that I was more interested in, right? So this is the part I actually wanted to know, which is disk-to-disk form factor approximation. And what they mean by form factor approximation here is that's from the radiosity terminology, I believe, which is what I wanted to know. So for two disks, I wanted to know what they were using for how the light transfers from one disk to another. Okay. And so you can see here, like, they have a little discussion of this. Disk radiance transfer function. We need to calculate the amount of light to reflect off the front face of each surface element. We compute ambient occlusion data first, which is, we're not looking at that just yet. If we first use direct lighting from point or directional lights, we compute the light at each element just as if the shading surface, including shadow mapping. We can also do both, blah, blah, blah. Here's the fragment program function to calculate element-to-element radiance transfer. And you can see the way they're doing it here is they've got the two normals, which we have both of. They have the emitter area, which, like I said, we don't really have explicit, but we know based on the level of approximation what its size would be effectively. And then we've got these two values they don't explain here. So they've got one, this is presumably a position, and then I'm not sure what D2 is, so we'll have to look. Okay. So what they do is they say the area of the emitter, the two cosines, which is again just that that sort of squishing that we were talking about, where as you get more oblique to something, the shaft of light sees less of the area. So we have the area of the emitter, both cosines, over pi times the r squared distance. That's the distance between the two. So I guess that's what this is right here. That's what the d2 is. Plus the area of the emitter. Now they didn't put a derivation in here, which is a little annoying. But we can at least see what most of it is. We can probably just look up distance transfer somewhere else, but we can at least see what most of it is. So if we have two surface elements, and we're looking at them like they had their diagram before, and here's our R, and here's our two normals, right? Then what we end up with in this case is we know that if they were directly facing each other, so if we had two disks that were directly facing each other like so, then we know that what would happen in that scenario is the full lighting transfer would occur. The angle would not be cutting down at it at all. But as we change the angle in both cases, less of the disks are seen in the visible hemisphere by the receiver, and less of the light is emitted by the emitter in that direction, right? So hence we end up with cosines for both of these in each case, taking the area of the emitter and scaling it down as a result. So that's like, this is the area that it would be taking up in terms of the like the hemisphere of incoming light. We multiply it by both cosines to take out the amount that the tilt is preventing it from doing so. And then we divide here by the pi r squared plus a. This is the part that I'm not sure about. Obviously, what we're taking into effect there is the distance that the emitter is moving away from you is going to attenuate how much, due to the inverse square law, we're getting. So pretty obvious here, the inverse square law is the r squared term. That's not a mystery. The pi in this case, I assume, is just because the area of the thing is a disk, so we end up with the pi in there. But this plus a bit, which is the area of the emitter, so honestly, no, that can't be what the pi is, because the area of the emitter is always already going to have pi in there, right? Pi is already factored into there. So I really don't know what the pi r squared is there. You know, pi r squared is the area of a disk, but it's the area of a disk if this was the radius. So I'm not really sure where exactly they got that denominator, and I would have liked to have seen it. Did they reference somebody here? Yeah, so I can't really see how they got that. Everything else makes good sense in there, but not that. And so if we take a look at how they're computing it here in the actual shader, where they assume that the emitter area has already been divided by pi, then what they've got in that case is they've got emitter area times cosine divided by r squared plus a, right? And so I assume what they did here is if everything in here is divided by pi, then you could just multiply through by pi. Of course, shouldn't that have given you a pi squared there? I mean, if we have this, so let's take a look here. So we have a cosine theta. Cosine. I'm going to use these like that. over pi r squared plus a. So if in this case what we're saying is we assume that a was already divided by the value pi. So to do that, we would have to divide both of these by pi. Okay, I guess I see how they did it. Yeah, that makes sense. So in order to divide both of these by pi, I'll just do it out so you can see it too. There's the divide by pi. So all I've done is divide all of these terms by pi, right? Because what I'm saying I want to do is do that pre-division by pi. Another way to think of this was I multiplied this by 1 over pi over 1 over pi, which is legal, right? I can multiply anything by 1, and it's fine. So if I look at what happens here, the pi's cancel here, and I end up with, and I can just associate this, right? So I can basically say, okay, I've got a over pi cosine theta cosine phi over r squared plus a over pi, and hey, there I'm down to just my two areas over pi. And then we get exactly what they said they would get, which is the emitter area pre-divided by pi, which is that, cosine cosine, divided by the r squared plus the emitter area already divided by pi. So that all checks out. So literally the only thing I'm not 100% happy with, like my understanding of what they were trying to say here, is the pi r squared plus a part. I'm just not sure what that's supposed to represent. And again, that's just comes from, I'm sure, working out the disk-to-disk radiance transfer in this case. The r squared makes good sense to me. The pi doesn't. I'm guessing that that must come from the solid angle computation. So, for example, I'm imagining that this surface is looking out at something, and I'm trying to figure out how much of this solid angle of the hemisphere this disk is taking up. The r squared part tells me what the projection is. The pi is probably coming from specifically that that solid angle calculation. I don't know if I can quickly find something that would confirm that. Oh, that's funny. Can we access this? Not very quickly. Well, maybe we won't read that paper. I just wanted to take a look at a disk-to-disk radiance transfer function so we could see, if I'm right about that being the solid angle part, and just so we could see what the plus A was exactly. Again, I'm assuming that that is from the solid angle computation. We should probably try to work that out at some point just so we could reassure ourselves that that is actually what's going on. But at least we know mostly what we're doing here and can certainly compute this pretty easily because we know what all the terms are, even if we're not 100% sure why they quite worked out to be what they are in the radiance transfer function. And again, this is just trying to say, so for a hemisphere, how much of the incoming light for this surface is going to come from, whatever this disk is up in the sky. The other interesting thing about this is we don't have to use a disk for any particular reason. We could really use any shape we want. We could use a sphere. We could use whatever. It just so happens that a disk is a nice element for being able to sort of just splat things in space and have them have a direction. Okay. So thinking about this a little bit further too, another thing we could try a little further on after we play with this a little bit is having our reflectors be disks and our emitters be spheres. If our emitters were spheres and it didn't hamper us too much in our ability to actually create the lighting that we wanted, which it might, then we would be in an interesting situation where we could not have front and back emission storage. So we could just have emission storage and that'd be it. And that would be pretty nice because that would get us out of the business of dealing with those extra textures. And it would also make it so that it was easier to conceptualize what was happening. When we averaged lights together, we would just be averaging kind of like spheres together, which is a little easier to understand than disks averaging together, where you end up with something pointing in a direction that neither of the two was pointing to before. That's just kind of a halfway pointing. Sorry, I got something in my eye here. So, there's something to be said for thinking about alternate ways of conceptualizing how the lights average up as they get higher. All right. So what we want to do here is we want to start getting the compute multi-light down to do something. And so in order to do that, we need to actually get it set up reasonably. And at the moment, we don't have that happening. So we need two things. One is we've got to be able to sample. So let's talk about what we need here. So we need the one level up. So we need basically our parent, and we need to get from our parent all of the values, right? So we need our parent for all of these. And then we need our neighbor. Right? So basically what we're saying is we're going to sample from the higher res version, and then we're going to sample from our res version. And then that would give us all of the data that we wanted, right? And we furthermore need to be able to do that neighborhood calculation very specifically. So we're going to need something better than frag UV here, right? We can use frag UV to sample from our parent, but we can't use frag UV to sample from our neighbor. But that's okay, because the neighbor is the same resolution as us, so that should be the easier case for us to handle, right? So then we get into this nasty business of sampling. We kind of get rid of this here. We get into this nasty business of sampling this whole ring of data values, which is going to be a pain in the butt, but that's just how it has to go. So what we want to do here is say, all right, we've got our parent front emit, and that's going to be sampling from the frag UV. And these are the only ones that have to use the frag UV, because these are the ones that are going to have to be blended. Meaning they're sampling up, let me go over here. They're sampling up to the parent, and that's not a direct sample. It's going to be an average of a few values. Now, in terms of the emittance, that upper level emittance that we're going to do there, so we got to think about this a little bit too, because this is actually somewhat complicated. So the sampling here is going to be a little bit different than what I drew originally. I was drawing something that was a little bit sort of simpler than what's actually going to go on. Let me draw this one more time, because I had not thought it through yet. So here we have the parent version of the texture, and here we have the neighbor version of the texture. And I believe what we want to do here is say, well, for any given person in here, we want them to essentially be able to sample from who is going to contribute light around them, but also further away, right? So in this case, what you can imagine is, suppose I'm doing a better person to talk about, for example, might be this person right here. We want them to take into account all of this lighting information that's right next to them, but we also want them to take into account the lighting information of all these other things that we don't have the computational budget to go ask about, right? So what we want to do is we want to sample from the higher resolution bitmap. Higher resolution. Lower resolution bitmap, higher sort of coverage. So what we kind of want to do is take samples of the neighbors for this pixel in the places that it's not going to check on its own. So I think that's roughly what we want to do, is say, let's use these three emitters and these three emitters as the emitters to use. And if we had to do 9, right? We could do 9, or we could do 4, right? We could just do the cardinal directions. So that's one thing we could do, is we could just do cardinal directions, but we do them on both grids. So we do it on the parent grid, we'll do it, and we do it on the neighbor grid. We just go one textile to each side on both grids. And then we consider all of those to be emitters. And the ones in the parent level are considered to be twice as large as the ones in the neighbor grid because they have been upsampled, right? So that, I guess, is what we would want to do. That seems like the more logical thing to me, yeah. So that seems like what we would want to do. And furthermore, we can, if we want to, we can still use bilinear filtering in this case, if we want to, for sampling the parent, so that we're really just talking about moving a certain delta in terms of the U and the V, and then we're just taking that, whatever that comes out, and we're assuming that that's the lighting contribution from there. Again, it's very sloppy, but that's okay. Again, we're just playing around with it. All right. So if you take a look at what's happening here, the parent, front, back, surface, and BTEC bit here, then when we go ahead and do the sampling for that, what we want to do is we want to take 4 texture samples there. And so what I'd like to do is I'd like to introduce a way to bundle these into a struct. I'm not sure to what extent I have the ability to do that, but I'm going to try. So let's say I said we have a struct light. Value. And a light value is going to be one of each of these things. So it's the front emit, the back emit, the surface color, the parent, or whoops, and the NP. And what I would like is I'd like to be able to say I want to get a light value from a function that's just like, you know, parent sample, and it's from a particular UV. And so what I'd like to do there is say I have a light value result. The result front emit equals texture at the UV. And so basically I'm just going to fill in each of these values by sampling from the corresponding texture. Now, looking at this, I don't think we need the surface color for these, right? And in fact, when we sample lighting values, we never need the surface color. The surface color is just for us to compute our own reflection. So I think, at least I think, we're never going to do anything with the surface color because that's already been stored into that lighting value, I think. And you know what else I think? I think we can ping pong this as well. So I think we could do this in 2 passes. The first pass does the computation that transfers the lighting down 1 level, and the next pass does the one that transfers it within a level. So probably the neighbor stuff doesn't have to happen, right? So probably compile multi-light down 0 is probably what this actually is, or maybe we'll have a multi-light down 2 because there's going to be 2 steps to this. All right. So in terms of taking the parent sample, then what we're going to say is like, okay, we're going to get all these values, but we don't need to know the surface color at all because the surface color isn't used for that transfer. So we're really only sampling from 3 textures, the 2 emitters and then the normal of them. So really this is what this looks like, right? So if I go ahead and say, there's my way to take a parent sample, then what I can do is say, well, I've got a couple of these. I've got the left version of it. Actually, it's just... And in this case, I don't know what the UV step is. So I guess what I want to do is say, you know, something like this. So basically all I'm saying here is like, yeah, we can get the neighbor, you know, the up, the left, right, the up, the down, from wherever we are right now. When we look into our parent, we can see what the neighboring values are by just looking using the U and the V step. Now, I'm going to call this UV step, and I'm going to do like .u, and .v, like so. Assuming that they allow me to do that. I don't know if they do. I guess I could just do X and Y. So we would need to pass in whatever that UV step was. I believe in shader version 4, you can just find out what that UV step is because you know the size of the texture. In our case, we don't have that, I don't think. I don't think shader 150 has that. I mean, I'll double check, but I don't think it does. Yeah. It definitely does not. I don't see struct anywhere in here. I sure hope we can do a struct. It's going to be super annoying if we can't make a struct It has nothing to do with the graphics card, whether you can do a struct or not, right? It's just the compilation language. Yeah, there we go. It's always hard to remember what you can do in each shader language version. All right. So we would need some way of getting this UV step in, so we're going to probably have to pass it down. Like I said, you don't need it in shader language 4 and up. You can just get this information, but we will probably have to just specify it. So we're going to have a uniform V2 here that's going to be the UV step, which all that is how far it takes you to go from one textile to the next textile in U and V, right? That's all we want to be able to do. So basically, when we go up to take a look at we go up to take a look at whatever our values are in the parent bitmap, we take where we would have been for our textile and we look to up, down, left, right. All right. So that's all we want to do from there. We can get rid of these entirely. And then if we wanted to do something really just dumb here, we could just average these values together, even though that's not at all what we're going to do eventually. Like I could say, okay, 0.25 times like left front emit plus right front emit plus up front emit plus back front emit. Don't know why I typed back there. There we go. And so that just produces another averaging step, which is not what we actually want to do here. We want to actually do the lighting computation here. But for now, we can actually test this by just throwing some arbitrary values in there based on the averaging. And so this would be the way we would do the downsampling from the parent, and then the calculation of the lighting for the neighborhood around us we could do as a separate pass. Now the interesting thing about this is this will still work. We'll still be able to. We don't have to do a neighborhood around us at the lower level. We could just always use larger emitters. And just leave it at that. So we don't actually have to even do that. We could always just take the lighting from our parent, and so at the moment, we can run the entire algorithm just this way and never use the local refinement step. So I'm going to leave, now that I think about it, I'll just leave compile multi-light down as the only thing happening at the moment, and let's just get this one working. So we know we have to do parent, back, and NP, and then we got the UV step. So let's get that. We don't have this one. The surface color is not going to be there. But what is going to be there eventually, so we might as well just prepare for it, is we do need to know two of the values here. We need to know what our NP text is, right? And we need to know what our surface color is. Because even though we're not using those yet, we will have to use them eventually, right? So because in order to compute the lighting equation, in addition to the lights we're checking against, we need to know what our reflection direction is and what our surface color is, right? So those two have to, be sampled. They don't have to be sampled from anywhere other than the exact current location. So we can just use a straightforward, right? I suppose these have to be that as well. So that's all the stuff we will need to compute the lighting equation. And then what we would do in here is do two evaluations of the lighting equation, one with the front values and one with the back values, right? That's all we would be doing there. And we can set ourselves up for slightly more success there by saying something like, well, okay, compute light or something, or transfer light. And what we want to do here is be able to effectively, evaluate each of these things as contribution. So in this case, we would end up with a situation where we wanted to say, all right, what's the reflectance color, what's the reflectance normal, what's the reflector position, something like this, although I'd probably pass them in the other order. So we've got the position of the reflector, the position of the direction of the reflector, and the color of the reflector. And then we would also do like, okay, what's the light P, the light normal, and the light emission, something like that. And when we do that lighting transfer, what we want to know is, this is where the disk-to-disk radiance transfer would be computed. Now, we're not actually going to do that at the moment. We're just going to take the result to be whatever the light emission was and assume that it gets transferred entirely, right? So the way this would break down here is we would need to call that transfer light for each one of these functions. So this is going to be kind of annoying since we have no indentation. But it's basically going to look like this, right? So we're going to say transfer light. We know we have, and we probably want this is the transfer light explicit where everything's been broken down. We probably also have a transfer light where we have just the emit and the NP for the light. Although that's not really true, I guess, because the NP has to be broken out anyway. So I take it back. I guess we don't really need that. Because probably what we want to do here is say, okay, let's actually break this out to the position and the normal, right? So we're going to sample the NP, but then we need to compute both of these values. Now the N is a pretty easy value to compute because since we know that the two values that we get in, the NP, X, and Y, are the actual X and Y values, we just need to take the Z value and compute that somehow. In order to compute that, we know the Pythagorean theorem, right? We know that this is a normalized vector, so it's pretty easy. We know that this has to sum to 1. So we know that the square root of nx squared plus ny squared plus nz squared has to equal 1. So if we square both sides, in this case, we just end up with this. And because 1 squared is 1. And so we just end up with nz squared equaling these two saucy gentlemen transferred over to the other side. Right? So you have nz squared equals 1 minus nx squared minus ny squared. And so it just means that this simple equation right here is all there is, right? So in order to reproduce this operation, we just need to take the square root of 1 minus nx times nx and minus ny times ny, right? So in that case, we just have a pretty straightforward operation to reconstruct the NPZ value, which then we do. The result p-value, on the other hand, is harder to compute. The reason it's hard to compute is because we have to do some real work there to figure out where it is going to be in world space based on strictly its location on the screen. Right now, I'm not going to do that. I'm just going to say that it's the NPZ value taken directly here, because we do know that that is going to be the depth of it. We just don't know what its x and y are. So I'll put to do in there, compute the x and y from the fragment coordinate. So that's all we really need to do there, and then we have the p and the n correctly. So then that lets us do transfer light as we would want to actually call it, right? We can just say left.p, left.n, left.front emit, and then we can just do ref p, ref n, ref c, right? So what we want to do is, since the transfer light is a summation in this case, each of the transferred lights, I believe, yeah, I can't actually line up like that because the indentation isn't ever respected, but each of these is just going to sum together. We're transferring the light from each of the places, so there is not any attenuation on it. So right now we'll take that approximate attenuation and we can throw it into here if we want to, but that's the only place that we should put it, right? So this is the reflectance color directly. That doesn't get modified. But these we have to compute. So the ref p and the ref n, these are the same. The ref n in this case is going to be and so since that's going to get done in both cases, I'm going to make that a function. So now we can do this reconstruct normal step anytime we want. And all I have to do is just pass in the texture sample, like so, and it'll reconstruct it. Furthermore, I could do reconstruct position, and the same thing. So that way, once we get this working properly, it'll just work everywhere, right? That one will have to take a UV as well. Guess I'll pass that second. It doesn't need it at the moment, but it will eventually. So we then have these two down here, which I'll do the same way. And now we have all the values that we need for our lighting transfer. So I can do the same for both of these. So now front and back are both included. Okay. So I think that's what we want here. Again, we've got 6 textures to sample from, all 3 of the parent values that deal with lighting, but not the surface color, and then just the surface color and the NP of the level that we're currently on, because we're going to need that. And then we'll write to the other 2, which are the 2 emission textures. So that, excuse me, should suffice. And now we just need to actually get those values out, like the bind locations out, and deal with all the compiler errors that I'm sure that we're going to have for this shader. So here's all the stuff we were specifying. So you can see here we've got parent front emit, parent back, parent NP, and then we want, so that's parent front emit, parent back emit, parent NP, good, that's good. And then we've got our NP, and our surface color. We then have the UV step. And those are all the things that we would have to bind for this particular one, as far as I can tell anyway. So all of that stuff has to get bound. And it has to have its own multigrid. There we go. It has to have its own information. Oops. That's not what I want to do. There we go. So here's our UV step. Here's our surface color. Here is our NP. And then here we just want our front emit, back emit, NP. And that's everybody. Yeah. So now when we actually get down to using this, we've got some work to do there as well. So when we do our multigrid up, which is here, when we do our multigrid up, we're going to do essentially the same sort of process in reverse, right? So during the downward phase, we're going to want almost exactly this. So what we're going to do is start at the top, and if the light buffer count, so you have to think about this a little bit. So the light buffer count tells us how many there are. If we actually accessed into that one, we would end up accessing into a non-existent light buffer, right? So light buffer count -1 is the index of the most simple light buffer we computed, right? It's the most averaged up. So what we want to do is we want to start at that one, and we want to propagate down to the lower level one. What that means is we are essentially going to be going backwards and be testing for our dest light buffer index, and this is actually the source right now. And we're going to test for our source to be greater than 0, right? Because when we get down to 0, that means that we can't go any further. That's already on that, we've already propagated down as much as we can. So we're starting at the top one, we're going to propagate down. So here this is exactly opposite of the upward pass. We've got the destination light buffer is whatever the source was -1, right? It's going to go down. So then we've got the source and the desc light buffers are both selected exactly the same way. And we're going to do another full screen fill. So all of this stuff is exactly the way that you would expect. So the only change here is what we are going to be binding, right? And so we want to bind a couple of different things here. The write all frame buffer is not the one we're going to use because remember, we're only writing to the emissions now. So we're going to use the write emit frame buffer, and it's a good thing too because we couldn't read from the surface color or the MP text for the dest, which we need to, if we were writing to it. So here we go. So we've got 0, 1, 2, 3, 4, 5 here. We know we've got front emit, back emit. We're not going to use the surface color, so we're just using the NP tech in this case. Oops. Okay. From the source. And then for the dest, we do need that surface color, and we do need that NP tech for the destination. So there's our 5 textures. We also need to specify, when we do our use program begin here, we also need to bind that UV step value. The UV step value is how far it takes to get from one textile to the next textile in the particular texture that we're looking at. And so since these things are essentially 0 to 1 mapped versions of the width and the height, we can determine this value very easily. So if we take a look at how we would do the source UV step, which is what this really is, and we probably should have called it that because it's different for the destination. The source UV step is going to be 1 over the width and height of the source, right? Because that's how far one textile would be in UV space. I don't know if we did a 1 over operator for our things. I'm not sure if that's true. It looks like we did. Oops. Here we go. So we did not do them. That's all right. And so the only thing I think we should have to do now, what is it complaining about here? GL texture 4 is an undeclared identifier. Is that so? Apparently that is so. Well, that's just ridiculous. Give me all of your textures. Or maybe not all of them, but let's take 8 of them. Okay. So that takes care of most of what we need to do. The only thing we need to do is make sure that we actually bind this stuff up. So we've got our use program begin for multi-light up. We basically need the same thing for multi-light down. And in this case, we now have 1, 2, 3, 4. So we've got parent front emit, parent back emit, parent NP. And those two. Then we also have a GL uniform to F. That's the UV step. It's probably 2FV, right? And we've got one of them. There we go. So we've got multigrid light up. Now we've got multigrid light down. We're all bound up. And so I think that should be all we really need to do. Yeah. I think that's about it for doing our our sort of reverse propagation. Now, we're going to have a lot of compiler errors here, and they're going to be hard to track down. Undeclared identifier n. Okay. So what are you talking about, undeclared identifier n? Well, I agree with you. It turns out there's not a lot of n there. Let's try that one more time. Undeclared identifier light. And that is a typo as well. What's next? Okay, that's not very helpful. Let's go ahead and continue stepping through there and see if we can get the individual validation errors. Function does not return a value parent sample. Okay. That is a very true statement. Undeclared identifier frag UV. Oops. This is true. I did not put in my smooth. I guess I must have accidentally deleted that when I was deleting the other things. This is a smooth in vec2 frag UV. That should be there. Undeclared ref C. Take care of that. All right, and let's try recompiling. Cannot convert from const float to high P3 component vector of float. Matching overload function reconstruct position. All right, let's take a look at that as well. Correct you are. Yeah. And then there's something where we're trying to make a float become a 3 value, which should not be happening. So we'll have to figure out why that's occurring as well. Oh, all right. Well, we're running now. But running is not particularly helpful, obviously, for a number of reasons, as you might imagine. Simply running is not going to get us very far. Let's take a look real quick at what these ended up being. Yeah. So there's our upward propagations. These are obviously not changed by the downward run. So as you'd expect, they're just fine. These, on the other hand, are quite a bit different, which may be correct or may be incorrect. We haven't really thought about it yet. I don't have time to do any debugging today or to really do anything particular with them, so we're going to have to kind of leave it as it is. But tomorrow, we will then be able to actually play with the lighting transfer and see if we can get some sort of crappy version of that working by the end of the day. Let's go ahead and do Q&A. There we go. Oh, and yeah, I did forget to do, these have to get replaced with left, right. Let's fix that. Just used. Have you seen the Doom 2016 rendering paper? I saw the slide presentation on it, but I have not seen I have an up in my downline. Thank you. I saw the slide, the presentation that Thiago Souza gave on it, if that's what you're talking about. Let me see here. Oh, Decius, this isn't a paper on it. This is the dude who does the reverse engineering the rendering process from taking the GL snapshots. Yes, I have seen it. I love this guy's stuff where he just looks at each of the frame captures. He's got one on GTA as well. That's good if you haven't seen it. Elite Tech, I'm on day 18 and I'm looking at the stream for the first time and I'm wondering what happened. I have these sweet colorful gradients and sound and all you have is 2 round circles. Well, we were playing around with lighting. If you want to see where we're actually at, we can turn off that debug render and draw actually where we were at. Which is to say that we're quite a bit further along in terms of tech stuff. But we wanted to do some light propagation work. So what we're looking at right now is just the reason we're looking at some dots on a screen is because we wanted to play around with some light propagation stuff. So we're just drawing those light propagation textures, if that makes sense. Shock 93, do you usually do a lot of programming before you run like you did today, or you program a bit and then run and debug? Is it because you know what you are doing that you take big chunks of programming and then run? Well, I run the program anytime I can. But sometimes you're doing stuff where you can't run it to get any meaningful output, right? So sometimes you might program for several days without being able to run the program because you're doing so much stuff that has to get into place before anything can happen. So I guess what I would say is I like to run the program. I mean, it's always useful information to run the program, but yeah, I just don't think that you're always in a position to. Sometimes it helps if you're trying to get through something. If it would take a long time to program and without running, you can try to come up with interim things. It's good to come up with fake ways to run the program, oh, I could just sort of stub this out. And you've seen me do that a bunch of times with lighting. You could have imagined us doing this in a very different way. We could have tried to write an entire lighting propagation system without ever running it and then running it, right? But we haven't been doing that, right? We've been drawing these little tiny steps along the way. And that is intentional because that allows us to check the state of the system much more frequently rather than just doing the whole thing, running it, it's not working, and having to go back and look at each component separately, right? Try running, now that we fixed the stupid error in the shader. Well, but I don't think it's really going to do anything differently. I mean, we aren't propagating light at the moment, right? We're just, we're just adding values together, so. Let's see. Traxy Rage. How long do you think this project is going to take? I don't know. Since it's a teaching stream, it's hard to guess. As long as it takes. Flag my name. New here. Sorry if this was asked before. If you were working on this on your own time, how long do you think it would take you to complete? Well, I mean, you can ballpark it just, the upper bound, right? Because the upper bound is going to just be the total time we spent on stream, compressed. So right now we spent something like, I don't know, is it 450 hours? So, I mean, I don't know how much you want to program a day. I would say 6 hours a day is a good amount of programming to generally do. So 75 days. If you assume that you were working 5 days a week, it's about 15 weeks we've done so far. It would probably go a lot faster if I was programming on my own, though. Like, it's probably more like 10 weeks or less, because if I was programming myself, I wouldn't have to be talking and explaining stuff all the time. And I mean, we spend huge amounts of time on the blackboard talking about stuff, and some of that stuff I would still do because I'd have to work it out in a notebook if it was that kind of thing, but most of it's just explanatory, and that all goes away. Do you think that game engines have a place, or is it just pure evil? I'm not sure I understand the question. I mean, how can you have a game without a game engine? Every game, in a sense, has an engine. Or do you just mean reusing the engine? Like something isn't an engine and it gets reused. Do you just mean the concept of reusing the code for like the core code of the game from one game in another game? I guess I'm just not sure what you're asking, because a game, every game essentially runs on an engine, which is the code necessary to do all the work that isn't specifically gameplay code, is typically how that's defined. So they're definitely not pure evil, because there's no I mean, what's the alternative? Do you have any good practice to keep your brain motivated after months and months of programming? I don't really ever have a problem being motivated to program for whatever reason. Like, I really like programming, so I always want to program. I would say the hard thing, the more difficult thing for me is usually, is really just keeping myself programming something specific and that makes money. right? If left to my own devices, I just program all day and I wouldn't necessarily ever ship anything. Or I might ship something, but it wouldn't be something that makes money. Like, you know, I might ship utilities, or I'd ship a new operating system or something. And, you know, that is completely something that can't make any money, right? So I guess I would say the only part that I find hard is defining a programming scope that is something that, when done, will make money so that you can keep living in programming. Forcing yourself to always be working towards that goal. And I don't have a lot of good solutions for that. It's hard, you know? But in terms of keeping programming, I've never had a problem. I always want to program. Like, every day I do it. And I've never had to convince myself to do it. Sharlock93, if we feed you sandwiches and keep you alive, what would you work on for the rest of your life? Well, what I'm working on at Molly right now is pretty much what I would want to do, right? If Molly survives as a company, then I will be pretty much set, like, because that's what I want to do. We make all our own stuff in-house, and it's stuff that I think needs doing. Well, Sherlock93, that's very generous of you, but we're not at that point quite yet. So I think we're good on financing until we ship 1935. And then if 1935 is successful, I think we're good. If it's not successful, then we'll have to think about what to do as a backup plan, right? So we may come with our hand out in exactly such a fashion. At that point, at the moment, we're okay. But I do appreciate the concern. Have you found the need to write certain algorithms directly in assembly for performance reasons? No, I haven't. But that's only because my interests tend to be much broader. So I tend to write large systems that are very intricate, and that's my focus area. I am not the kind of person who tends to focus on wringing the maximum performance out of a particular piece of code. That's like what Rad Game Tools does, for example. And I can tell you they definitely have written things directly in assembly for performance reasons. Because they often hit times when they know they can do something better than what the compiler is outputting with, say, the intrinsics. And they will have to drop to assembly to get it to do those things. Because they just can't get the compiler to output the right string of code or whatever, right? And I have had that situation when I was working at Rad. I did have that situation. I did do assembly language optimization for some stuff on the Xbox 360, for example. But that was the only time I really did it. And that's also one of the reasons that my optimization knowledge for x64 isn't great, is because like my optimization knowledge for 360 was very good. Like I beat their compiler by I think they were twice as slow or 3 times as slow on like some filter kernel stuff I had done than the assembly language that I ended up generating. I had like a Metropolis optimizer thing I wrote. And that thing was pretty cool. So I had a lot of understanding of how to optimize that machine. But I don't have a lot of understanding of how to optimize like the x64 because I just haven't done it. So like I have a vague recollection. I mean, like when we did it on this stream, like someone had to tell me about IACA. I didn't even know they had shipped such a thing. And looking at how it worked took me a while to understand exactly how the x64 port stuff worked and that sort of thing. So I just don't have a lot of experience with that. And so, you know, I would have to be more experienced to begin with in order to get to the point where I felt like I needed to take control away from the compiler and go to assembly for x64. Slow any word on getting other programs to work on some code on Handmade Hero? Sean, I'm assuming based on the spelling of Sean there, you're talking about not Sean Barrett. But maybe you are talking about Sean Barrett for graphics? Which Sean are you talking about? Anyway, but you said Adult Hour Edition, which I guess could be either Sean, because I think they did that together. For graphics, Fabian for Propagation, John for game design, Sean to dance. Oh, you had the other Sean in there as well, to dance and party. Does Sean Barrett dance and party a lot? That is news to me, if that is true. I know he drums. He plays the drums. I don't know that he dances. He could play the drums so other people could dance. Although I know he likes odd time signatures, so it might be hard to dance to Sean's drumming. But I don't know. As for the actual gravamen of the question there, or I guess I shouldn't say gravamen because you're not complaining. But the heart of the question, let's say. I don't know whether people will want to work on the code or not. I feel like, in general, that sort of thing would probably be more comfortable for other programmers to give me something I could use. So, for example, if I asked, you know, Fabian or something to give us a compressor we could use to compress our art pack file or something, right? And he streamed development of that compressor, that might be a more comfortable thing for someone to do than here's a code base that's not your code base and now you have to work on it all of a sudden on stream while talking, right? Just seems kind of like a big ask, you know. One of the reasons I'm able to do Handmade Hero and explain it as I'm going is because I'm doing all stuff the way I do it and the code is all familiar to me because I wrote it all, right? And that makes it a lot easier. If you're sitting here reading the code trying to figure out how something works all the time because it's not your code and you don't, you know, recognize it, that's, you know, I feel like that's pretty tough, right? And probably not much fun was the other thing, right? Reading other people's code is usually not much fun. You do it because you have to learn from it or to modify it. But it's not the fun part of the problem, obviously. So you know stuff about 360 hardware. How much of a problem was in-order execution? Did that cause performance problems? Do you view out-of-order execution as the performance convenience it claims to be, at least with respect to instruction-level parallelism? So, I guess what I would say about that is that it really depends. I would say that out-of-order execution and in-order execution are not, there is not a strict one of the two that is better. And the reason that there's not a strict one of the two that's better is because it very much depends on what kind of code you're running. So if you are running code that you understand very well and have optimized very carefully and which works on very predictable workloads. So for example, shader code. In the earlier days, when it was kind of rote sampling from textures and writing to frame buffers in a very understood way, that is something that is very easy to do as an in-order execution model because there's almost never a mystery as to where the memory bubble is, right? You always know when you're going to stall because you know exactly where your fetches are and you know exactly how long they're probably going to take in most cases. So in circumstances where you have workloads like that, out-of-order execution is strictly a waste of core space. You should have just stamped down more in-order cores if you can, because out-of-order cores are typically much more complicated. However, if instead you start looking at more modern graphics workloads that involve things like ray tracing and unpredictable kinds of queries into the memory space that are very difficult to know whether something's going to complete in 16 cycles or 300 cycles, suddenly out-of-order execution may become a little bit more attractive, right? Because you might not be able to really figure out exactly how the memory bubbles are going to line up. And it may be that dynamic arrangement of code execution is the only way to get around that. Now that becomes even more true when you start talking about things like AI code and game code, where we're walking arbitrary structures in no particular way. Who knows what's going on, right? And it's very hard to predict when you're going to hit a memory stall, but you know there's going to be a lot of them. Again, out-of-order execution may really be a win there. So I would say it's very difficult to really predict whether in-order execution or out-of-order execution is better for a CPU without really being able to test it on the workloads you want to run. I think that's why you see, a console can get away with in-order execution and a PC can't, because a PC is running such varied workloads and is a moving target that changes over time as the processor evolves. Asking programmers to optimize memory bubbles to a moving target like that, I think is just going to fail. And so I think that's why out-of-order execution makes sense on the PC, because it has to be there in order for the ecosystem to work, even if in isolation, if you just took one SKU of the chip, it might not make sense. If everyone could, and all the compilers and all the programmers could optimize just to that one chip and know that that was the only chip, then, in order might suddenly be okay or something like that, right? So my statement on that is just that in order isn't that big of a deal in my experience to work around if you're talking about looking at a specific workload, optimizing to that specific workload, and the workload is somewhat predictable, and you only have one chip, suddenly it's pretty plausible. When you look at the broader case, it just becomes a lot less a lot less tractable to do that and still get high performance out of the chip if you don't have those things. And I think that's basically all I had to say about 360 hardware. I mean, the thing about the PowerPC at that time was it also had the load hit store penalty, which is a real pain in the butt. So you had to be really careful with the way things got read and written. I would say, if anything, the load hit store penalty was the much worse problem with that chip than in order execution was. Because the load hit store penalty was a lot like in order execution, in the sense that load hit store penalty is easy to avoid if you know specifically what workload you're doing and the code that you're working on. But once you start talking about things that operate like cross-function, all of a sudden load hit store becomes a lot harder to avoid, because load hit store penalties inside a particular function you can analyze explicitly. And you can go, okay, I know that once I store to something, I can't ever load from that thing again until, I can't remember what it was, like 40 cycles or something like this. So I know that I just need to go look at the cycle, because the other nice thing about in-order execution is the cycle counts are perfectly predictable. So you can look through the assembly code and know exactly how many cycles you have until you could load from that address again. So that's really easy to avoid inside a particular function, because you know all the parameters. And easy is a little bit weird because, easy, it could be hard to structure the code in the right way to make sure it doesn't happen. But easy in the sense that you know whether it's happening or not, and you know what you need to do to fix it. However, cross-functionally, that becomes a lot more annoying. So now when you talk about like a function calling another function, and it's getting called from multiple places, well, if this function is going to load something at the start in order that, from some shared thing, a structure, global structure, whatever, if it's going to load something that might have been stored by the caller recently inside the 40 cycle window, well, now you're going to get that load hit store penalty. And that's much harder to analyze, right? Because now you have to look at a call graph. And, modern programming tools just aren't set up to let you do stuff like quickly iterate on what the assembly language layout of all the things in your code that call each other are and look for load hit store penalties, right? Like, you're talking about really special purpose tools for that sort of thing to make that convenient that just didn't exist. And so the load hit store penalty, I would say, was actually considerably worse than the in-order thing, but they're sort of two sides of the same thing. They're both two stalls that can occur that an out-of-order processor wouldn't have, because when it hit that stall, it would just switch to the next thing it could execute down the road. All right, last question. If you had SIMD code for SSE2 but also had the same algorithm for AVX 256-bit, is there a way to run only the AVX in the shipping version if the hardware supports it? Must it be decided at compile time? So the answer is yep. There's two ways you can do it. They're both basically the same. But one's a little more drastic than the other. So when you start your program, you can do a check on the CPU type to see, because they have capability flags, you can do a check on the CPU type to see whether or not it supports AVX. And then you can set your function pointers to point to either the SSE2 versions of your functions or the AVX versions of your functions, right? So you don't have to do it at compile time. You can compile both versions and then just jump to the correct version. Now, the other thing you can do, if you just don't want to deal with it at all, is you can actually write your program in two parts. And so Handmade Hero is kind of already set up this way, right? So Handmade Hero, when we launched the game, there's actually a Win32 executable that loads a DLL that has the game in it. So what we could do very simply on Handmade Hero, right, is compile the DLL in SSE2, compile the DLL in AVX 256, as you say, and then at startup we just check in the Win32 executable which one we have, and we load the corresponding DLL. And that just lets the compiler optimize everything it wants to optimize, even stuff you didn't optimize. If it wants to, it can, depending on your compiler, whether it supports anything interesting there. That's a way to just have everything compiled, SSE2 and AVX, and then just pick at runtime. So you've got two ways. One's like fine-grained, one's coarser-grained. With the way Handmade Hero is set up, I'd say just use the latter, because then the compiler can use AVX 512, for example, even. You could have one version for each, because AVX 512 is a really good instruction set. When compilers get better at making AVX 512 code, they could do some really great stuff. So I would say, that's probably the easiest and best way to do it. Is just make one DLL for every chip and launch the right one at startup. All right. Too many windows. All right. Thank you, Ed, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series yourself, you can always pre-order the game on handmadehero.org. It comes with the source code so you can follow along at home. We also have a forum site you can go to if you want to ask questions, a Patreon page you can go to if you want to support the video series, a schedule bot you can use that tweets the schedule at you, so if you want to catch us when we're live, that's the way to find out, and an episode guide that you can use to figure out what we've done in the past very quickly. It has a nice search feature now too, so you can just drop to anywhere that we've talked about a particular topic, you can jump straight to it. That's about it. I will be back here tomorrow. I will be back here in 23 hours and 9 minutes, as you can see. Tomorrow's time will be noon, Pacific Daylight Time. We'll be playing around with that lighting a little bit more to start to get the lighting transfer working, and yeah, hopefully we'll end up with something that's at least somewhat usable. Possibly tomorrow we'll have something that's not doing any shadowing, but that kind of does a little bit of transfer. And then the next weekend we'll have to start looking at maybe doing something that's a little smarter about how things get shadowed and other stuff like that. So that's about it. Thanks for joining me until tomorrow. Have fun programming, and I'll see you on the internet. Take it easy, everybody.